a lot of time with today is a simple molecule. We use 2-bromobutane plus strong base. So we're going to use 2-bromobutane plus a strong base, and some of you should already be able to kind of anticipate what types of products we will have. I'm just going to draw the products right away. It's a little bit premature to do this, but I'm just going to draw them here. Some of you might already be able to guess these, and we're going to work our way towards making all three of these products. Okay, we're going to have 1-butene, trans-2-butene, cis-2-butene, and all three things are formed from this reaction, which you should be able to infer from the pre-lecture video that I gave over the weekend. Let's talk a little bit about what strong base is and how to make it. So again, we're going to spend a lot of time with 2-bromobutane, but let's talk about how to make strong bases. Just for fun. So to make sodium hydroxide, something like sodium hydroxide, it's actually a really simple process. If you take sodium metal, I have about 1 kilogram of this stuff about 50 feet away from me. It's kind of this soft, malleable, kind of clay-like material. So when we have a metal with 0 here, it means it's in the metal form, as opposed to an ionic form, right? Where these are ions in solution, a salt. This will be a metallic form, and sodium metal is very soft. You can literally cut it with a plastic knife or a plastic utensil. You can easily take a spatula and cut right through it. And if you drop this in water, you're going to have a heck of a big explosion. But if you do this really carefully, you can mix water, sodium hydroxide, sodium metal, and you get sodium hydroxide plus half an equivalent of hydrogen gas. This reaction is very, very exothermic. It generates a lot of heat. So when you take a big chunk of sodium, throw it in a pond, don't do this, it starts generating a hydrogen right away, and lots of heat, and the hydrogen catches fire instantly from the heat generated from the reaction, and you get an explosion. This is a powerful base because it's the conjugate base of water. So this obviously classifies as a strong base, which you learned in general chemistry. We can do this with other molecules. We can take sodium metal again, and we can take ethanol. Waste a perfectly good molecule of ethanol on this Monday morning. Ethanol is slightly less acidic than water. This is about 15.7, it's about 16. So it's less acidic, so if you make its base, it's a slightly stronger base. You can make sodium ethoxide by this method. And again, if we balance the reaction equation, we get this is not mercury. This is hydrogen gas, H2. You get half an equivalent of H2 for every time this reaction works. So this is a general technique we use to make these things. We can use other metals like potassium. Potassium is much more reactive. It's quite a dangerous metal. I have a little bit of this floating around somewhere. Potassium you can melt almost on the heat of your hand or body temperature, maybe a little bit higher than that. And then so you have this thing that looks like mercury, liquid metal, that's, if it finds any water in the air, it catches fire instantly. So this is great fun for the family. Good thing they don't just sell that to anybody, just people like me. But we can make other bases. Potassium T-butoxide might be a base in your notes or in some of the problems you encounter. And again, these are decreasing acidity, so slightly increasing basicity, since the pKs of these compounds are going up little by little here through here. So we have these types of 3 bases. They're very, very simple to make using this process. Nothing too serious about it. Okay, we're going to get back to our example now after I've segued away from it. And let's revisit our molecule of 2-bromobutane. And we're going to react it with sodium. Let's use sodium ethoxide, the one we just made today on the last slide. So we're just going to look at these 2 things together. Now, this is normally thought of as a substrate, right? And you might already be thinking, oh, it's a secondary substrate. This is all true. But we're going to see this molecule and identify it by sight that it's a strong base. And so it's not going to be as inclined to do substitution reactions as it is to do elimination reactions. So again, this is confusing. I get it. But work through our work today as if we're doing elimination reactions. That's what I want you to practice and think about. If your mind keeps going back, oh, I want to do SN2 to this, just calm your mind for a minute, just relax, and just focus on what is an elimination reaction, how do they work? And the way we approach these, when we mix these two things together, we're going to use this technique I developed with us for carbocations. We're going to call this carbon alpha, this carbon beta, this carbon beta, and then we're going to look at these, all the carbons attached to alpha. And if they're different, we're just going to label them differently. Okay, I'm just going to call one beta 1, one beta 2. And the way that we work out these problems is we will write expanded molecular formula at all beta positions. We're going to write out expanded molecular formula at all beta positions. This should be a familiar exercise for us when we were doing carbocation rearrangements. So let's just start at the beta 1 position. What I mean by writing an expanded molecular formula, I'm going to rewrite bromobutane, but I'm not going to write the whole thing in an expanded molecular formula. It's very cumbersome to write all these bonds out. But at beta 1, I'm going to draw it out in expanded molecular formula. So these two portions of the molecule are an expanded formula, where all the action's happening. This here is kind of in a condensed molecular formula. By all means, you could write all these bonds out if you want, but it's a little bit cumbersome. And here we're really going to focus all our attention on beta 1 position and this alpha position. Okay? Let's draw our base molecule nearby, and then let's have a short discussion about syn and anti. Okay? So the mechanism for this, we've seen a few times. We're going to practice it here, but it's base attacking this in an acid-base reaction. Electrons start moving towards the leaving group, and they form a double bond here between alpha and beta, and leaving group leaves. The required geometry for this molecule is that one of these hydrogens and beta has to be anti or syn. So we have to have, let's just focus our attention on this hydrogen here. We could use any of them, and this one here. We could use any hydrogen at this beta position, they're all equal. But do you think that these two things can line up in anti or syn arrangements? Keep in mind that we have this carbon-carbon single bond, and about this carbon-carbon single bond here, we have free rotation. So at this kind of bold bond here, I don't know exactly how to color code this. I don't want to make it too much of a mess here. But this particular bond here, we have free rotation. Right? Means we can rotate this 360 degrees all day long, and the molecule at room temperature actually is rotating and moving around almost violently, very, very fast. We take a very fast camera to get a picture of this molecule where it's frozen in one conformation. It's rotating very, very fast about this bond. So the point is, about these linear types of molecules, we don't really have to be too worried about anti or syn. Of course we could get to an anti conformation. Of course we could get to a syn conformation. We're going to see this issue come back a little bit later, but for the time being, we don't need to draw this in Newman projection. We don't need to draw this in Sawhorse projection. There's free rotation about here, so eventually this hydrogen is going to line up 180 degrees or 0 degrees. So here we can make a note. We don't have to draw Newman. We don't have to draw Sawhorse. This hydrogen and this bromine are at anti or syn conformations repeatedly all the time. Okay, so we're not going to draw them here. But instead, let's draw this mechanism. Let's draw it in a red pen. It's going to be drawn with our typical 2-electron arrow. We have to draw this one next, and we have to draw this one last. Okay? And from this series of arrows, I want you to just draw the product that you would predict from it. Okay? All the clues are here, all the answers are here. You should be able to draw. What product does this describe? If you're awake, and if you studied the pre-lecture video at all. So this would make 1-butene, right, at the beta-1 position. The key things for us again, we're going to have a substrate with a leaving group, and now we're reacting with a base. We turn our attention to beta positions. We just explored this beta position, we make this particular product. So now we're going to explore the other beta position. If we pull off any of these other hydrogens, doesn't matter, we'll always get this. We can pull off this one or this one, they're all going to lead to this particular alkene. No other products possible from beta-1 position. The beta-2 position, let me see if I can just leave this here a little bit. Beta-2 position, we're going to do the same thing. We're going to expand the beta-2 position. And we're going to leave the alpha position expanded. So here, this is beta-2, this is alpha, and I've just expanded those two carbon atoms. It just makes drawing all these reaction mechanisms a lot nicer when we can see all the bonds. We're trying to do a reaction on this hydrogen. It's hard for you to describe what bonds are breaking or the electrons are moving from. But when we see all the bonds, then we can easily indicate this. Let's actually draw our base off to this side. We could draw it anywhere. And this is our beta-2 position. We have two different hydrogens here. And the question is, can this hydrogen or this one, can it ever get 180 degrees oriented to this bromine or 0 degrees oriented? And it doesn't matter which one we look at. This bond here has free rotation. Rotating wildly. You could build it with model kit and see for yourself that this is rotating and flipping. Do you think ever this hydrogen can line up 180 degrees with this? Or maybe 0 degrees with this? It's even kind of suspicious. I drew this kind of almost as 180 here. But of course it can line up, right? Or this one, the way it's drawn here, looks like it's sin, but these two hydrogens can absolutely line up 180 degrees, which is preferred, or 0 degrees, which is also acceptable. So we don't have to draw this molecule with any more detail for the time being. Whenever we have these linear alkanes, or alkyl halides, I should say, because since they have a bromine attached to them, they absolutely always can get to a syn or anti-conformation. Let's actually pluck off this acidic proton at the beta-2 position. The electrons start moving towards the leaving group, and then the leaving group leaves. And in this particular drawing, we're going to get to cis and trans alkenes. This drawing doesn't describe that we made this one or this one necessarily. We will get to that issue later. Okay? For the time being, if you, on an exam, only happen to draw this alkene, I'm hoping you would draw both, but if you just drew one, doesn't mean you lose 50% of the points. On an exam, this mechanism matters, this is a beta position, this mechanism matters, forming an alkene matters. That's the bulk of the points. Drawing this little extra guy here isn't necessarily 50% of the points. It's probably a trivial or small amount. So if we miss a few things on the exam in this fast-paced course, don't draw every single product. It won't be the end of the world for you. But when we make this double bond in the middle here, this 2-butene, we should know that there's two stereoisomers for it. We have this huge combination of products now, and it turns out that when this reaction is run, you isolate about 20% of the 1-butene, and this combined mixture of cis and trans, you get about 80% yield. This is an experimental number. Don't need to memorize it, but something emerged from this type of early research, and that was a trend, and the trend is the thing we have to work towards. The trend is that more substituted alkenes will be favored as the major products in these types of reactions, and that more substituted alkenes will be more stable than less substituted alkenes. It's kind of a strange type of rule. It does have a name. This is about the only rule I like to put to paper. It's called Zaitsev's rule. A very famous Russian chemist whose name no one knows